Well, thanks for being here on a rainy Friday before spring break. I thought I'd make today a more casual lecture, probably give you some homework hints, think about some homework problems together, stuff like that. And I thought I'd tell you about a good book to read if you found this subject interesting. Kind of book you could read over the summer if you wanted to. After this class, I read it, or a lot of it, as an undergraduate at Michigan and found it an inspirational book. Anyway, I'll tell you about it in a minute. Before I start thinking about some homework problems with you, I thought I'd expand on that last thing I did last time. Any questions about anything? Or requests? So that thing I showed you at the end of the last lecture, it was a consequence. We had two facts, namely let's see, this picture is actually f as a mapping from the interval AB into R. So a continuous function on a closed interval. So the fact was, if f is continuous on a closed interval, closed is important here, then f maps the closed interval to a closed interval. So in fact, f of I is equal to m, little m, capital M, the closed interval from the minimum to the maximum. And of course, if those two things are equal, then that means the function's constant. And it's still true, the image would just be the 1 point closed interval, which we allow, where the endpoint is the same as the starting point and end point are the same. That's just a singleton point. That would be the case of a constant function. And we allow that. So, where M is the min on the interval, and capital M is the max. And in the proof of those things, those min and max are the same as the inf and the sup. Equals the same as the inf, and equals the same as the sup. Well, there's something in the book calls the preservation of intervals theorem, and it's more sophisticated than this thing. Well, let's see, I should say why this is true. There were two key facts. In this setting of a closed interval, we know the min and max are assumed. The min and the max are attained at points. So those get hit. And then that other key feature so number one is this. Number two, the intermediate value theorem. Every value between the min and the max gets hit. That fills in the rest of the interval. Well, intervals in the real line are analogous to convex sets. Convex sets in R2 are more interesting, a lot more interesting. Convex sets in R2 are such that if, let's see the definition. What happened here? Sorry, fix that. R2. So a convex set in R2 is a set such that, give me any 2 points, A and B, in the set, then the line joining A to B is also in the set. So there's a line. So the definition of convex set in R2, let's call this set S. S is convex means if A and B are in there, then the line connecting them is in S. Well, it turns out that the notion of convex set in R2 is exactly the same as the notion of interval. So a convex set in R interval. Let's see, there's an interval could look like AB. It could look like AB or AB or AB with various kind of endpoints included. The A and the B are like the boundary of that set. And so that set I drew in the plane is an open set, and then the green thing is the boundary. And whether or not the boundary points are in or out is, in that case, would be a weird thing to think about, because then there'd be lots of points could be either in or out. But in the case of an interval on the real line, there's only 2 endpoints. And let's see, these are the bounded intervals. You would also have the whole thing. You could have minus infinity to a point. You could have minus infinity to that kind of thing. Or you could have point B to infinity. Or you could have B included to infinity. Ones on top are the bounded intervals. So a fact that I skipped over from the previous section is that an interval, let's see, that is characterized by the feature is the kind of the convexity theorem fact feeling. So I is an interval if and only if for every pair of points x1, x2 in the set, then everything between x1 and x2. So let's see. Let me call this S. A set S is an interval if and only if for every pair of points in S, the interval from x1, let's take x1 less than x2, or less than or equal to. the closed interval from x1 to x2 would have to be contained in S. That's kind of like a feeling for the intermediate value theorem for sets. If 2 points are in, then everything in between them is in. Okay, and then you get all those possibilities up there from those definitions. And of course, the bounded sets, the bounded intervals, would be the inf of the set, and the B would be the sup of the set. And the inf and the sup are either in or out. And so then you get all those possible cases above there of the endpoints are either in or out. And when you go through all those cases, you basically prove this fact. Anyway, I don't want to make a big deal out of that proof. And sometimes you could have bounded from below. That would give you the plus infinity sets. And bounded, bounded from below would allow you to go out to plus infinity. And bounded above would be the minus infinity example sets above here. And of course, neither would give you minus infinity to infinity, the whole real line. Well, the fancier version of the theorem I started out with is called the preservation of intervals theorem. And it is, if f is continuous on an interval, and not necessarily a closed interval, then f of I is an interval. And not necessarily a closed one. In fact, there's no easy way to characterize the nature of the image knowing the I, except in the case of a closed interval. Then closed gets mapped to closed. So, remarks. The proof is just the intermediate value theorem. And this notion of convexity that we have now in the one-dimensional case. And the closed to close is the only easy case. This is the only straightforward case. All the others get jumbled up. The rest get jumbled. In fact, I'll show you a nice, quick, easy way to come up with lots of situations. So let's do some examples. My favorite example is the sine function. So the sine function wiggles up and down and has maxes and mins. So there's the origin. This is a graph of sine of x. And it's wiggling up and down between +1 and -1. So if you think about why don't we think about, let's let this sine of x is f of x. If you think about, how about f of the open interval from minus pi over 4 to plus pi over 4. That would spit out an open interval. And the lower endpoint would be minus square root of 2 over 2, and the upper endpoint would be square root of 2 over 2. So there's a case of an open interval getting mapped to an open interval. But if I take it going from minus 2 pi to plus 2 pi, or how about minus pi to plus pi? That would be even easier. That would be fill out minus 1 to 1. So there's an open interval getting mapped to a closed interval because of the maxes and the mins, and they're attained in there. And I could come up with pretty much anything I want now by playing around with this idea. That, if I take a short enough interval that doesn't have the maxes and mins, I can avoid getting the endpoints in there. And as soon as I go over a max and a min, then the endpoint gets included in the image, etc. And another idea is if you have a function that blows up. Well, let's see. Let me think of another weird one. Could I... terrible things could happen, like if I had sine 1 over x. On, how about 0 pi? It wiggles, it's continuous on that open interval, it wiggles like heck, and it would map also to the whole closed interval from minus 1 to 1. Those weird things. And how about just 1 over x on 0 pi? Let's see, that would map 0 pi to minus 1 plus 1, including the endpoints. And it would hit those endpoints infinitely many times. And this one would map 0 pi, let's see, it blows up. So it would go to, let's see, the smallest thing it ever gets is 1 over pi, and it would blow out to infinity. Anyway, you can come up with all kinds of examples where they get jumbled up. Question? Will the 1 over pi be included or be open? Let's see. Oh, you're right. 1 over pi doesn't get hit. Thanks. Anyway, I don't want to go through all the cases, but they're all straightforward applications of that fact about intervals characterized by that property. It's very reminiscent of the intermediate value theorem, except for sets. So in some of the homework, you'll be asked to come up with examples that do various things. Let's see. Let's think about one and just play around. How about page 133, number 3. We want f and g to be discontinuous. Find f and g discontinuous. They say actually at a point with f plus g continuous, and then part B is, or f times g continuous. Got any ideas about how you might go about doing that? Yeah.
For the f plus g, you just choose like 1 over x plus 1, and then negative 1 over x plus 1.
Exactly. Yeah, f plus g is, that's a good, so he says try 1 over x plus 1 and 1 over x minus 1. Wait a minute. What'd you say?
No, have the minus 1 at the top, so like 1 over x plus 1, negative 1 over x plus 1. Like opposites.
Oh, yeah, so when they add up the, yeah, so in fact, that kind of idea is if I take f plus u plus g minus u, the u's cancel. So let's say you want f and g, wait a minute. Yeah, so this would be a new f. And this would be a new g. All right, so I want, what do I want? I want these things to be discontinuous. So if I have little f and g being continuous and u not continuous, then I could do this trick of adding and subtracting. So you could have fg good, u bad, and then the capital F and the g would be bad. Could I do something similar for the product? They're both. They have the additive group and the multiplicative group. Wouldn't be surprised if you could come up with similar ideas there. Let's see, I could have f times g equals f times 1 over g. Let's see what I want to do here. F over g equals f times u over g times u, and the u's cancel. It's the multiplicative group, and I'm putting the inverse in the picture. In the top I have the additive inverse, on the bottom I have the multiplicative inverse. And so you could have f and g be good, and then you could multiply by a u that's bad, and you'd have to be careful about g being not vanishing. But you could do the similar trick there, I think. Any other ideas about how you might go about doing it?
Make them 0 and multiplicative 1. Make g 0 and f not 0.
That's a good idea. But let's see. Oh yeah, whenever you multiply by 0, you get 0, and so that the problem is 0 is continuous, and we want the g to be discontinuous. But the 0 idea is a very good idea. So I'm going to call this ideas. Those ideas would work, I think. But the classic function that just goes totally bonkers, everybody's favorite function, let's call this f1 of t, or x rather, is 0 at the rational numbers and 1 at the irrational numbers. And if you think about, okay, what would I have to add to that one to get rid of the discontinuities? And it wouldn't take long for you to think of the idea of filling in the you can fill in the bad spots by making it 1 at Q and 0 at the rest. Those are discontinuous everywhere. And when I add them up, I get something that's 1 everywhere. That's continuous. And when I multiply them together, I get something that's 0 everywhere. That's continuous. So that would be one way to do. That's like a way of stomping on the problem. But there's a million ways to go about doing this. Let's find an example. I think this is another one of the homework problems. Find an example where f is discontinuous. They're at a point, or everywhere would be more fun, but the absolute value of f is continuous. Got any ideas? Yeah.
Can you do the same equation instead of 0 and make it -1?
Exactly. Replace 0 by -1 above. That would do it. And you can always do tricks like that. Like I could have something be x squared when x is rational and minus x squared when it's irrational. Then it would look like it's bouncing around. But when you take its absolute value, it would always be x squared. Stuff like that. Any other questions about the homework you want to talk about? Probably haven't had a chance to look at them yet. Homework 7 is due the Wednesday after break. Don't save it for the last minute. I should have been urging you to try to finish it before you go on break. Anyway, that's a hint for a couple of the problems. And now I'm going to give you my advertisement for this wonderful book. Your summer reading if you like this stuff. It's called, I always thought it was pronounced primer, but after meeting the author's son, it's a primer of real analysis. And instead of dwelling on, our book by Bartle is very, what's the word I'm looking for? It plods along and does everything. And this book skips the everything part and wants to show you the sort of fascinating, interesting things. And that's why it's a fun book. It's by Ralph P. Boas. Who was a famous complex analyst. And I went to school at MIT with his son, Harold Boas. And Harold wrote an updated version. We were both students of Norberto Kurtzman. Anyway, it's a wonderful book, and let's see, there's some fun facts in there that blew my mind. They show using something called Baire category. They show that most continuous functions are nowhere differentiable, and they say exactly what they mean by most. Most continuous functions are nowhere differentiable. And the proof uses something called bare category theorem. The bare category. Which is explained there and is a cool thing. They do. What else do they do that's fun? Oh yeah, so we touched on the notion of cardinality of a set, Cantor's idea. So in this book, the cardinality of 0, 1 interval is the same as the cardinality of 0, 1 cross 0, 1. So there's the same, think of it, the same number of points in the interval as there is in the square. You'd think of the square as being a heck of a lot bigger. But it turns out, so what does that mean? Cardinality means there exists a mapping from 0, 1 into the square that is 1-to-1 and onto. Okay. That's a mind-blowing thing. In this book, they actually explain why how to do that and think about it. But a even more mind-blowing thing. Let's see. So there's one fact. There's no continuous function that does that. But there is no continuous phi that does that. Not hard to see. And an even bigger but, there does exist a space-filling curve, a continuous space-filling curve that maps 0, 1 onto that thing. There is a continuous space-filling curve. Phi that is onto. It's not 1-to-1. And the way it's constructed in the book is that there's some points that get hit up to 5 times. So it's fun. It's less than or equal to 5-to-1. So yeah, a point might have 5 preimages, but no more. And if you want to see beautiful pictures of how space-filling curves are constructed, it goes back to Peano. The same person who was thinking about the axioms of the real numbers. It's a mind-blowing thing. You get polygonal curves, and you have this way of doing like a fractal. You see what they do on one square, and then you cut that into a bunch of little squares, and you add more and more microscopic repeating things, and you show that the limit function makes sense and is continuous, and it hits every point. So it's a really cool thing to think about, and mind-blowing. that you can map a one-dimensional set and fill out a two-dimensional set. Of course, it's not differentiable either. So you certainly can't do that in a differentiable way. And that brings you to another subject that you might have heard about is Brownian motion. Brownian motion is a related thing. It's when you look at it under a microscope, it's highly discontinuous. It's like Brownian motion was what they looked at a little particle in a liquid and realized it was getting bounced around in a weird way because of the vibrations of the particles around it. And so it's constantly getting buffeted in various directions and tracing out a very weird non-differentiable curve. And you can turn that into a science of cooking up non-differentiable curves. That's fascinating. And you need to use analysis plus probability theory to study those things. Let's see. What else was I going to do today? Let's think about another one of the homework problems. Page 134, number 8. This question says G is continuous. So no, F from 0, 1 to R I've got two functions. F and G are functions on the closed interval 0, 1 to R. And F of R is equal to G of R for all the rational points. Then the question asked if what was it? Is that what this is asking? Okay, they agree on the rational numbers. Oh. I guess it's kind of this is sounding like a dumb question to me. Is F the same as G? What would you say to that question? I guess our examples above where you play around with, what would you play around with? Yeah.
Is it said that F or G is continuous?
No! That's the key here. That's why it's in this section on continuity. Being continuous would make this let's see. This is an obvious no because let's think about, we could have F be our favorite one. We could have it be 1 on Q and 0 on let's see, could have it be 1 on the rational numbers, and have it be 0 on not the rational numbers. And if G, you could make it just be 1 on all of them. And those would agree on the rationals, and they wouldn't be the same. So that's kind of a dumb idea. But your observation that O, if one of them is continuous, then this changes the whole situation. Or let's see, what do we have to know? We'd have to know they're both continuous. Would we? Yeah.
So is this question 8 on the,
That's question 8 on page 134.
okay. Maybe I have it the wrong
Wrong edition? Mine is the 4th edition.
Oh, okay.
You might have been doing the wrong homework all semester. The books are different, yeah. But if F and G are continuous, then of course the rational numbers pile up everywhere. And so if somebody asks you to demonstrate this, but if F and G are continuous, then yes. And that's, let's see, so we know they're equal to the rational numbers. You would pick an x naught that's it would be irrational. So it would be 0, 1 minus q. That's irrational. If I ask you to prove this, what would be the most obvious thing to do here? Yeah.
I guess the obvious thing would be like, if f of the irrational is not equal f of rational, then you could find a subsequence of rationals that equal whatever value.
Yeah.
And then that would be non-continuous.
Yeah. So, exactly. So remember the sequential characterization. There was a word for it. I forget what it's called. The sequential definition of continuity. F is continuous at if and only if every sequence converges and is equal to L. So it's continuous at x naught if and only if f of xn tends to f of x naught for every sequence. In the set whose limit is x naught. Okay, so if I just find one sequence that where that doesn't converge, then I would let's see. So I want to show that they are the same. So I'm going to look at f minus g. That would be 0 on the rationals. And we know the irrationals are dense. Let's see, now we know the rationals are dense. So how would I cook up a sequence? Any ideas? Here's my x naught. How would I get a sequence that tends to x naught that's rational? I want to toss out an idea. I guess I don't do this often enough, and I should have gotten you in the habit of dying to toss out your idea. Ah, I like that idea. 1 over n. Yeah, but that's exactly the typical thing to do here. If I take x naught plus 1 over n, then I have 2 points, and the density, remember, meant there's always a point in between. So the density means give me any 2 points. There's I could find a q sub n between those two. And then because 1 over n goes to 0 as n goes to infinity, that's exactly what you need to show that the qn tends to x naught. I get a sequence qn with qn tending to x naught, and f minus g is continuous, and it's 0 on that qn. So the limit, as n goes to infinity, of f of qn minus g of qn, they agree on the rational numbers. So that would have to be equal to 0. And that would be equal to f of x naught minus g of x naught if it's continuous. So that's how you would use the sort of tools that we have at our disposal to nail that idea. Okay, that feels like enough for today. Any last minute questions about anything? Well, have a good break. And thanks for being here today.
Maybe like I have read the wrong book, but I mean I don't know if you like a mix of a 7 and 8, or if
Oh, they are continuous. What did I say?
I think like you did.
I'm seeing double here. That's my problem.
Yeah, like a mix of like 7 like an 8, and I was like, oh, okay, like I guess it's
Okay, yeah. 8 is they assume they're continuous. So yeah, I guess I didn't assume that just so we could think about it.
But I think like it was so helpful, like just like
Okay, good. Yeah.
Okay. Did you happen to get a chance to look over my exam problem?
Oh yeah. I think I fixed it in the grade book. Did you notice? Double check to make sure your score got changed in the grade book.